Today we want to discuss basic concepts for classification. Our agenda, as you see in front of you, is we want to talk about the basic concept, decision tree induction, Bayes classifiers, rule-based classification. Uh, we provide some model evaluation and selection, how to select a model, and then techniques to improve classification accuracy. The concept here is we can have in classification two approaches. One is approach with the supervision, which basically I supervise the classifier to be trained or to gain some knowledge for the samples I'm trying or the data I'm classifying. And once I build this classifier with this knowledge, I will input the new data, which will be following the same trend as the previous classifier. On the other hand, we have another approach which is called clustering, which basically I will label the training data to be unknown, and I will have some measures and some abbreviations, which basically I will go to the training data and say, here is the information, figure out what kind of classification or what kind of clusters you should be able to see. There are two issues around the prediction for classification. One is classifier itself, how to categorize the data and how to create labels. We want to construct a model for the data. We want to look at different attributes. The other one is numeric, which basically the classification is supposed to be a continuous function. So we will we have to figure out solutions, which we talked about before. How to find out missing data, how to find outliers, unknown data, and different aspects of the data. Here we give a general umbrella, and in this general umbrella, we will be able to provide more specific once you have a specific approach. So if I want to understand the process basically is we have a model construction where I construct the data, and I will be able to figure out what kind of characteristics I need, what kind of labeling, what kind of classification rule I may have. We will explain a few different rules in a few minutes. The other one is basically I will have the model usages, which basically I estimate the accuracy, I can test, and I can build my classifier. So this figure in front of you here simplify the process. So we have basically a training data sets, you have a classification algorithm, and the classification algorithm will build the classifier model, and then you will have the results. So for example, here, when I look at the number of years, it will find out that if rank is equal to professor or year greater than 6, tenure is yes. So I'm here looking for characteristics. What does it mean tenured, which is yes and no here. I can also use the model for prediction, which basically I can put information like the green record here. It's a testing data. This is testing data, which is not being seen before the model, and then I can find out the classifier. For sure, you had some lectures in deep neural network and neural network and other aspects where you have some hands-on, and we will have in the project another approach to have this hands-on examples as well. If I want to move to the second approach, the second approach is I will talk about decision tree induction. So in decision tree induction, I will be basically having a training set. I can build a tree. So once I classify the information over a tree, I can figure out which ones are the one which is rolling, and which one is the one which is to the left and one to the right. You have to notice that this decision tree is always recursive. So the minute you start to put this data in, you start to classify this data in a way. So decision trees are, as you know from the algorithm courses before, they are basically a greedy algorithms. They are top-down recursive. They are divide and conquer, because basically I divide the problem into two different problems. So here I am looking for the problems of students less than 30 years old. Here is more than 40 years old. So it's basically I divide and conquer. At the start, all data are at the root, and then I will start to build a categorization or splitting criteria to create the tree. I can also have decisions to stop the tree at the bottom. So we have some questions about how much data do you need. So basically we have, this is the amount of information required, and we call it entropy. So if I have information to be set into the classifier, it needs the amount of information will be equal to sigma I to m pi log pi, and this is the log to the base 2. And this is the actual complexity level of building the tree itself. So if you have the information less than that, you will not be able to construct the tree. Now, when I have the splitting, the information will be at the ratio. So if I have the splitting here, the information on the right-hand side will be equal to the information to the left-hand side. And in this particular induction rules, I'm looking at binary trees. So if I want to have how much information I gain at each attribute, it will be the information, the full information required to construct the whole tree minus the information of the branch itself. This will give me the gain information. So if the probability pi be the probability of the arbitrary tuple D belong to a class C, estimated by C of ID over the D, and D is the full size of the class, and C, sorry, D is the full size of the information, and the C is the size of the class itself. So the amount of the class or the number of elements in the class over the whole class. In this way, I will look at the expected information as info d sigma pi log pi. As I repeat again, the information here will be the splitting between d, j, or d, which basically, if I have the branches, the probability of the amount of information I have in this branch divided by the amount of information over the whole branch, or over the whole set, this will give me the detailed or the gain for this data. So from this perspective, I can compute a new definition called the gain, and the gain will be the information itself minus the amount of information needed for D, and this gain will give me basically, I would say, the gain of adding this branch is the whole set minus the gain of adding of the other branch. So this amount of gain is another factor we have to consider. So if I want to say, I want to give a very short example. So I have a data sets here, and these data sets will say, I want to create a class P where buying a computer is yes, and the class N, which is no, buying computer equal to no. I can, using this information, I should be able to compute at different age level, which is age from less than 30, more than 40, and between 31 to 40. I will be able to compute the probability, and I will be able to compute the gain of each element. So here I can have the gain of income, I can have the gain of student, I can have the gain of credit rating, and in this way I should be able to compute how much contribution of this element. So if I get a new member, for example, and I know this is specific information, I'll be able to understand in my classifier how much data I can receive, or how much information I can receive if I will have this particular gain. So The other aspect of data, usually we talk about single data or discrete data, and we talk on the other side on continuous data. So if I want to look at some sort of continuous values, so the continuous values, I will be basically using a midpoint or a possible split point, or you can call it averaging, and using the continuous values attribute, you will be always look at this midpoint, which basically is a point which segments the data left to right. And from that perspective, you can still compute the data using a similar approach. In this particular approach here, you look at DJ, or the actual, this is supposed to be the probability of the data, because it's for every subset DI, you look at the size of DI over the whole set. So this will be P, and this will be log 2 P. So basically the equation will carry. However, the definition of the P will be a little bit different, because basically it computes the probability, not the probability, it computes the actual value at this particular point. Then here we can look at the Gini index, and the Gini index is another approach where they basically have it's 1 minus sigma p square I, p square, and p is the relative frequency of the class. So what are they looking for here is they trying to figure out some metrics. So once they have a classifier, you can decide how much cost, how much computational time, how much value, how much memory, how much delay. So using these particular different factors is an example of how this computation, and this computation can be done based on different ideas or different researchers early on, and they try to figure out this metric. So Gini is another index, and if I want to compute the Gini, I will be basically say D has 9 tuples in Bine computer. I'm using the same example which I used it here, which is basically the same example of the computer buyer. Okay, so here I have D, and D has 9 tuples in the Bine computer, yes, and 5 in no. So basically the gain will be 1 minus 9 over 14, which is 14 is the whole population, and then square, and then 5, and the results will be around 0.459. So if I have if I suppose the attribute income of partition D into 10 into D1, which is low, and 4 into D2, the Gini income will be equal to 10 over 14 times the Gini of D1, 4 over 14 times the Gini of D, supposed to be D2 here in this case. So comparing attributes, so we have what we call it information gain, we have gain ratio, we have gain index. Here you have some comments like information gain will be biased toward multi-valued attribute. Gain ratio will be prefer unbalanced split, and Gini index will be based on multi-value attribute, and it has difficult when number of classes is large, because basically you will compute different classes, and in some other context we talk about having correlation between these different classes. Always the question is, how do we expect to have a question here? It's basically giving one example like this example, or which is basically the same table as this one. It will say, given this table, please compute information gain, compute gain ratio, and Gini index. In the literature, there are so many other attribute criteria, like SHADE, which basically SHADE is a popular decision tree algorithm which is measured on X-squared test for independence. CSAB, it performed better for than information gain Gini, and for some cases there is G statistics, which is close approximation of X-square distribution. There is a minimal description length, multivariate split, and these attributes will be giving good results. None is significant superior than the others. Okay, if I wanna just say, okay, do we have to study this, all of these other attributes? The principle is no, because you should be able only to understand the basic ones, and these basic ones will allow you to, if you understand how to compute each one of those, you will be able to understand how these ones will be performed. Number two is why there are so many. There are so many because basically it's like statistics. We have average, we have mean, mod, stochastic, different criteria to compute different aspects of relation between numbers. So basically it's the same here. Is you have the class and the class size, you can have similar criteria basically. Now, the biggest question will be is, once I have this tree, you can have multi-classifiers here because you basically can achieve the same distribution of data based on different criteria. So for example, if I say less than 20, and then I will say 30, I will say, or if I say 35 here, and then when I go splitting here, I will say the group class of 25 and 30. So I can have there are multi ways to reach the same results. So if I look at this, here there are two different concepts. One is overfitting. So overfitting means if I have a tree or I have a splitting, the tree is a decision. So if I have decisions and the decision will split too many, it means I have too many decisions to make. So if I have too many decisions I make like a human being, I can get confused. And once I get confused, I will have anomaly, I can have noise, I can have outliers. So for example, to give you an idea here, if I decide to change this to have more than one splitting, I'm here concerned only with students, which is less than 30, and I'm looking at 31 to 40. So if I say 35 here, and I will be less than 35, and then I can do a further splitting, and I have a baby, for example. So the baby will be included because my computation is from 31, which will be sub of this class. So once you have the data distributed in this way, you may have a tree overfit of training data, which basically have too many branches. Too many branches means also that the subset or the subset of the data here will be smaller. So one can ask, okay, so how can I build a good classifier? We have to balance the trees as the leaves. So if the leaf will be only one element each time, or a very small number of elements like 1 to 3, and you have 1,000,000, this will be a very forest tree. We call it forest tree because it will have too many splitting. If I will have too big of a class here, so everybody is here, this will be a very shallow tree, and then I will not be able to classify. So the two concepts we have here, one is called overfitting. It means too many branches, and these too many branches can reflect anomalies, can be suspicion to outliers. Remember, the outliers definition was data which does not fit. It can also have a poor accuracy for unseen samples, and this is if you talk about prediction. So we can do pre-pruning, which basically is like a tree. You have a tree at home and you want to prune it. Prune it means you cut some branches or you merge some branches together. So we can halt the tree of not splitting nodes if the results will fall below a specific threshold. And we can have also something called post pruning, which basically I construct the tree and I will be able to reallocate or rearrange the data or remove some of the data once the tree is fully constructed. So outfitting means data has so many splits, so many branches, how do we know it? It's a qualitative approach. So you have to have knowledge of the actual information. So it's just when we talk here about specific examples, the examples come when you have the example, because here we just talk about a concept. So we in a decision trees, there is something called outfitting. Outfitting means you have too many branches, and it will create poor accuracy, and it will reflect anomalies because you have noise, you have outliers, you have data which does not comply with the general data. You have how to fix the overfitting by two ways. One is to one way is to mainly pruning. Pruning means cutting the unnecessary branches. So as in nature, you can do a pre-pruning because you can basically terminate a branch before it starts in a tree. Or you can do post pruning, which basically cutting the branches after you have the full tree. You can have some enhancement to the basic decision tree induction. One of them is to allow for continuous value attributes, which basically we can dynamically define discrete values, and these discrete values will represent some interval inside the continuous variable. Now, this will be discretization. So I basically take a continuous value and I will be basically make it discrete representation. We can also talk about, which we described before, about missing data. So how to handle missing data. So missing data, we can predict the data, we can compute the probability, we can compute the average, we can figure out techniques to fill missing data. We can create attributes based on existing ones. That is, we can basically combine, or we can build the classes. So I can go inside some data and say, okay, instead of figuring out this particular edges, I will create a class of multi-edges. And this particular attributes, it's called replica, or fragmentation, or repetition, which basically I can build these classes to enhance. Now, these classes, when I build them, it means also that I'm very aware of the data. I can analyze the data, and I can figure out the best model to fit these data. So I have also classification in large database. So if I want to look at classification in large database, this problem is very well known. It can be done by statistics, and it can be done by machine learning. The more data you have, usually the longer time to find a solution for. So the problem with the large database, it has scalability. So basically you have multiple attributes, and these attributes, you want to examine them. The whole concept of indexing was basically to avoid processing this data to create different views of it. So if you want to understand what they mean, classification in a large database is basically running an SQL, or running a query over specific attributes, and this query will be an approach of how to build this data. So if I have the query, I can use the query language to process this data, which is basically a simpler way, because if I have a query, I will not need to process the data in a different way. I can use the exact language. The problem with processing this data, basically it's tabular data. Because it's tabular data, it means that I have this data in a tabular form. And if I fix the data to a tabular form, it will not be the general data which we talk about when we talk about data mining. So you can see here we talk about rainforest algorithm, which has been introduced in 1998. And this rainforest, it basically create multiple attributes. It create a list of attributes, value, and then class label, which is an approach of doing indexing in a different way. One notice for you here is if you look at these particular concepts, you have to verify what are the dates of these particular concepts. So If I look at, give some comments on the scalability framework of a rainforest, it basically, it separates the scalable aspect of criteria that determine the quality of the tree. So basically I can build an attribute value class label list, and this attribute value class label list, I will create the set, and the set will be, I can project the training of the data sets onto the attribute X, and from that point, I can build what we call it the ABC group, which basically the predictor of all attributes within a specific node. To give you an example here, I have the training sets, which is the same training sets of the students buying a computer, with the credit rating. I can build the ABC here, so the ABC set on ages, the ABC set of income, the ABC set of student decision, and the ABC set of attribute rating. You may notice that here the decision is binary, so it's either yes or no. And then I will have this frequent table. So this is a data set. So if I want to examine, I will examine this particular data set. If you forget about the data mining at all and you look at it from different angle or different perspective, you will realize this is a way of building what we call it complex index, because I can index, if I assume this is a database, or this is a schema in a database, or a table in a database, I would like to build different indexes here so I can point to specific. So here it creates a specific index to this data. The biggest challenge here is if you add a new set, what will happen? You have to go back and modify this data. There is one thing I want you to see as well is here, for example, you have it has 0 element. So this 0 in a different examples or in a consequent techniques, it can create a problem. So usually we avoid having a null or a 0 element in any of these trees, and we basically shift them by adding 1, and which is a technique. We'll explain it in the last section of this lecture, where we will talk about how to enhance the computation and how to avoid the errors. So this is a training set. This is the rainforest training set. So here I have the sets. Now, if I have any element and I will examine, I will be basically, instead of examining the whole set here, I will, if I have an age, I want to know how, if somebody, what is the likelihood of somebody will buy a computer based on his age. I will only examine 3 records instead of examining all of these records. If I want to know it's a students or not, I will examine 2 records. And if I want to compare the complexity level of this example to the other one, the other approach is basically you will go inside the tree and you try to figure out the decision trees as well. So ABC is an example of statistical computation compared to decision making. And from that point, we will be able to reduce or to process the data in a reduced way. There is also another techniques for optimizing the different algorithms. So now what I'm trying to explain here is what are the techniques to be able to figure out decision from the data we have. So there's a famous technique called bootstrapping, and bootstrapping is a technique where I will be able to create representation of the data which will fit my memory. So which is bootstrapped optimized algorithm for tree construction. So boot is basically a statistical technique used called bootstrapping. Each subset is used to create a tree. It results into several trees. So these trees are examined and used to construct new form of tree. And the new tree will be very similar to the original tree. The advantage of the bootstrap is basically required 2 scan of the database, and it's incremental algorithm, which means that every time you have a new element, you don't need to re-examine the whole elements. It's basically, you can add in 1 at a time. So here, this is a presentation of the bootstrapping. That's okay. For example, if I want to go here and talk about bootstrapping, each one of these trees or structure, it can split into multi trees. So basically, this is an example of the bootstrapping where the tree will have multi elements, and then from these elements I can build. Here is the view of the visualization of the decision tree, how it looks like when it has lots of subtrees. This is another visualization or class of visualization, which basically, if I will take any sector, I will have all the elements which basically inside the sectors. So until this point, we talked about decision trees. We talk about the basic concept, and the basic concept was basically two things. One is I want to classify or I want to cluster. Then we talked about decision trees and how to optimize the decision trees using strapping or using AVC approach. As I always say, this particular data mining course is basically hands-on. So one or two of these different techniques, you will exercise them inside the tutorial. You will have them inside the project, but you will not be able to see all of them. However, you should be able to study and be able to know how to compute the information gain and how to compute the other things. So basically, the next section I will talk about it is the Bayes classifiers, and this is I call it Bayesian classifiers. And Bayesian classifiers is a statistical classifier. It's always about the Bayes theory. The Bayesian classifier, naive Bayesian classifier, have been comparable performance to decision tree. It's incremental, and even if the Bayesian has large computation, there are some ways to optimize it. What I want you to understand at this point is, I have a classifier. Okay, so what I'm looking for inside a classifier, I am looking at a classifier which can predict. It has some formulas, most likely it's probability. I look at performance. Performance means what? Performance means how often or how long do I have to wait to get the results, or how long will it take to build the decision or the tree. So the Bayesian classifier, it's always comparable to decision tree. So why we always compare to decision tree? Because decision tree has the lowest level of complexity, because once you have a decision into multi-levels and you talk about P log P, it's a very basic, it's most likely the smallest boundary you can work with. You always look also at a classifier which has incremental. So incremental means any new data will come to, will not push you to process the whole data again. So it's not recursive. So prior knowledge can be combined with an observed data. This is what call it incremental data. So if you've been asked how can you compare between these two different classifiers, it's very straightforward. You have the statistical classifiers or rule-based classifier. Rule-based, basically like the tree, when the tree will be based on which one or which things, which attribute or which ages. So the other one is performance, which basically how long will it take on the average, or how many classes or how many tests I will do. Is it incremental or not? Basically, if I have a new element, do I have to retrain? Or do I have to do something else? Now, coming to Bayesian theory, Bayesian, I believe you had the same lecture, the same Bayesian theory in a different courses before. Basically, if you have the X is a sample or the evidence or the class of unknown label, H is the hypothesis or that X belong to a class. So the classification is what is the probability of the X belong to this class. This is a conditional probability over the given its H. So what is the probability of H given X exists? And in statistics and probability, we call this as a posterior probability, and the probability that this hypothesis hold given the sample X. So PH, because if I take PH given A, BH given X, the likelihood of H if the element is X, this will be equal to an equation where you have PH, you have divided by BX over BH, one of these equations. So PX given the likelihood of the class itself, it's called likelihood. Px is the probability that the sample data is observed or is correct. And if I want to look at how this equation will be computed, so given training data set X and the probability Ph of given X follows a Bayes theorem, and the Bayes theorem will be Ph over X will be equal to the probability of X given the class H time Ph over the probability of the observer, which basically this is the equation, and which is basically the likelihood, which is Px over H time the prior evidence, which is the probability of H given the probability of X. So to predict this particular X belongs to a specific class, you would be basically replacing the H with the specific class. So in this way, we will be able to compute what is the probability of this training data, and then we will allocate the data to the one which has the highest probability. The problem of the Bayesian classifiers is you need to have knowledge of the probability of the data. So you need basically to know what's your data. It has a significant computational cost because you have to imagine that whenever the class will grow or with any new data, the whole H and Px over H will change. So having a prior knowledge of the data with many probability, it will basically, this is the practical difficulties of the Bayesian. There is a naive Bayesian classifier, and the naive Bayesian classifier, it's driven from the Bayesian theory, and basically it uses the formula of multi-classes, and the probability of the class will be basically, I'm replacing the H in this particular formula to be the class Ci. So the probability of a specific class Ci that's X belongs to this class will be equal to the probability of X given Ci or the class times the probability of the class over the probability of X. So if Px is constant because the observation is always constant, then I need to maximize the Px Ci time given Ci time Pci. So this is the derivation of the Bayesian naive classifier, and you may want to consider it to read it. However, it couldn't come in an exam because basically the tutorials and exams will be online, so we don't have any way to write equations, which is an advantage on your side. However, you should read it at least once. So here I want to apply the Bayesian classifier over the training data sets of the students buying computers. So I will have C1 will be the students buying the computer, yes. C2 buys the computer, no. The data sets, the data samples age less than 30, income equal medium, student equal yes, and the credit fair rating. Then I will compute the probability of Ci, which is buying a computer, which will be equal to 9 over 14, and no computer buying 5 over 14. I will compute the probability of Bx over Ci, which basically the age, how many of them are less than 30 and buying computer, how many less than 30 and not buying computer, how many have medium income and buying computer, how many medium income and not buying computer, and then the probability of being a student and buy a computer, and then being a student and not buying a computer, and from getting all of this probability, I will be able to compute the probability of X over Ci, and then I will be compute the Bayesian, and then therefore if X, if it's 0.00, for example, X will be belong to the class buying computer equal to yes, because both probability here, this one is much higher. So you should be able to figure to understand how to compute or how to get how to compute a Bayesian classifier for the exam over an example of similar size. So here is the X, which is the question, which is if somebody aged less than 30 has medium income, he's a student, and the credit rate is fair, which class will belong? Will he buy a computer or not? So by computing the probability here, we will find out that the probability of buying a computer is yes is 0.028, and the probability of buying a computer no is 0.007. Because of these probabilities, this fellow will most likely buy a computer. So I would encourage you to go back to this slide 34, and from slide 34 you remember this equation, or you get this equation, and then you figure out, given this data set, how to do the math, how to compute it, and from that point you should be able to figure out the decision. The main issue in this probability, naive Bayesian or any of this probability, is basically you have a zero computation. So you may end up having a zero. So to avoid the zero computation, you can always add one to each case. So for example, remember there was a zero probability, a zero individual here. So there was this zero data here, which is somebody between 31 to 40, it's zero. This population of zero may create a problem once we start to have the computation. So basically, what we will do here is we will add one to each case. So the probability of income low, it will be one, not zero. And by adding one to each case, if there is 1,000 students, we will be basically having 1,003. And so here, suppose the data set have 1,000 tuple, you have low income of zero, medium of 990, income of 10. So the total income is 1,000, but you have an income of low zero. So you should be able to add one to each class, which basically increase the population of 3. Now, if in a different context, we talk about this particular element, that there is always a limitation if you want to build a classifier, that the class has to, for sure, have at least one element. So if the class has to have one element, at least one element to exist. So there are some other techniques for classification, which we talk about. If you have a class, you must have a class of element. There is no class which has no element. If you have a set, there is no empty set. There is no null set. So if you have this condition means what? This condition means that if you have one set, which one element, so you start with the assumption that's how many sets do you have, or how many different classes you have, and you add an element to each class, and from that point, you would be basically to avoid the zero computation. So there are some comments on the naive classifier. One is the advantage is easy to implement. It's good results obtained in most cases. Disadvantage, it has conditional independence. It's loss of accuracy. It's practical. It depends on existing among variables. So basically, how to deal with dependency, we will care about it in chapter next chapter, in chapter 9. So basically, there's some advantage for the naive Bayesian classifier. The following, so we discussed right now some basic concepts on classification and clustering. We talk about decision trees, and we get some computational boundaries for it. We talk about Bayesian classifiers and how you can use the probability approach. Right now, we talk about the third techniques, which basically rule-based approach. So in rule-based approach for classification, we talk about if then else. So if these rules exist, or this particular attribute exists, then it will belong. Otherwise, it will not belong. The issues with rule-based classification is you may have more than one rule which conflict, or more than one rule which does not trigger the same, like it's had a conflict between them. So you'll be basically having a rule-based, and if you have a rule-based techniques, you will have a rule list, and the list of rules, it can describe priorities of which rule has to be applying first. Once you have a conflict, you have to give, there are so many techniques to work on the conflict. One technique is basically to have the rule, value or rule power, like an index. You may have the rule as also as priority. So you say if this rule applies, the other one will not be applied. So if I will look at the same example we have, and rules are easy to understand than larger trees, because you basically can understand. So the rule extractions of this particular tree, it will say if age is young, which is less than 30, and the student is no, then buying computer is no. So if I look here, the age is young, which is 30 here, and the student is no, so the answer is no. The other one we will talk about will be the same. It will be like if the rule is young and the student is yes, the other he will buy a computer. If middle age, he will buy a computer, because there is no condition. So anybody between 31 to 40, they will buy a computer. If 40, now if I look at these particular rules, and you have to understand that the following rules are like in this particular case are else's. So if the first rule will not be concluded, you have to go second, third, fourth, and fifth and stuff. So the order of getting this rule based, you have to understand that the sequential may have a problem, because you don't know which rules. You always have a rule at one time. Each time the rule is learned, the tuple is covered by the rule are removed, which basically and the process repeat till the tuples terminate conditions, or you run out of rules. So so rules have different techniques, and if you want to extract these rules from, like what we're trying to explain here is how to extract the rules from the algorithm. So basically I have here this tree. I will get the first rule. So the first rule will cover the age, will cover student, will cover no and no. This one on the left hand side. Now, or the leaf at the left hand side. Now I did not cover yes and yes. So I will go basically and figure out how to cover this green yes, which is the second element. So if I have the rule for it, I will basically cross it. So every time I figure out this rule, I will be basically cross this particular element. I will cross this one. I will cross this one. I will cross this one. And with the last rule, I will cross this one. So once you have all the leaves or all the decisions crossed, it means you have a complete coverage between the rules and the data set. Let's just remove this annotation. Okay. So, so this sequential covering, it's a way, and there are algorithms for different covering techniques. So you make sure that you have your data fully covered. There is also some sort of sets. So here, basically, I will target the tuple to the left. I will generate the rule. I will remove the positive target tuple to satisfy the rule. And I can be basically creating subsets like that. I can have positive examples means examples which meet the criteria. Negative example means element which doesn't meet the criteria. So here's we talk about how to build a rule. So you start with the most general rule. You try to add attribute to accommodate the depth first strategy. So basically, I will start here from the age, and then I will go depth first. So I decided to go in this way first. So I will go depth, I will go student. Then what's after student, I will figure it out. When I finish this branch with the two rules, I will go to the second one, and the second one will be age 31 to 40, it will be yes. The last one will be greater than 40, then credit rating yes or fair. So I will go in this way, and I can start the rule based on greedy algorithm and I will go depth first. I will pick up the most improved to improve the rule quality. Consider both coverage and accuracy. So FOIL gain, in FOIL reps assess the info gain. So I will be able here to process the info gain, and which means which rule has the best quality here. So this rule or this rule. So the question will be, if I cover with this rule, will I have information gain or not? And the one which has the maximum information gain will be the one which will be able to get to extend the condition. In rule-based approach, you usually also look at problems where do you have a big rule which cover more leaves, or you have multiple rules, and how many rules. So there are rule-based classifier is a outstanding research models, and you still people are trying to come up with different rules to fit different classifier. We have two more topics to cover here today, and one will be the model evaluation and selection. The other ones will be techniques to classification accuracy. So in model evaluation and selection, I wanna how to measure the accuracy and how and what metrics, what kind of metrics you have to consider. So using a test set, you can have a class of tuples, and the class of tuples can be labeled, and you have number of frequency and number of accuracy, and you can compute frequency, you can compute accuracy. So basically, how to estimate the accuracy. Basically, there are some techniques to give some measures. None of them is accurate. There are some sort of handhold techniques, random subsampling. You can do a cross validation. You can do a bootstrap, which we explained in a little bit details prior. If you didn't see it, please go back to the recording and you'll watch it. You have comparing classifiers. You can have confidence interval. You can do cost analysis. So these are different techniques for selection. So if I look at confusion metrics, confusion metrics is one classifier evaluation, which basically, if I have classes and not class. So here I will say this is the actual class and this is the predicted class. And please, when you see these four terms come out, take you for your mind the data mining course. This is a very general term for accuracy in life. So the thing is, the actual class are to the row, to the columns. So C1 and C and not C here are the actual classes, which basically the events happening in real life. And labeling them or predicting them to which class will be the one on this particular row. So if I say true positive means what? True means it's a true class, and the positive means I predicted that's belong to the true events or the true classes happening. True negative means I have a class which is happening and I did not predict it in the proper class. False negative, it means I cannot see this particular event. So in any predictor or any classifiers, if you cannot see the actual event, this is an attribute which is usually we don't use, because it means that I can miss events, I can miss threats. If I want to detect if somebody coming to the room and I say I have false negative means somebody will come and I will not be able to decide that this one come to the room. If I want to say I want to detect vehicles coming through the street and I have false negative, it means when the cars come to the street, I will not be able to see it. So false negative, it's always no. False negative is somebody who will never be using this classifier. So usually false negative, we don't talk about it too much. True negative, on the other hand, means I don't have I don't have an event, and I will have, I will say I don't have, it does not belong to this class. So we always look at true positive and true negative as the one. False positive means I don't have an event and I will belong it to this class. For example, I'm looking for vehicles coming to the street, and the system will say there is a vehicle, but when you look at the recording, you will find no vehicle there. This is called false positive, and then you can examine. Common classifiers in detection, for example, if you have wind and rain and shadows, and the shadow will be seen in front of the camera as human or as a vehicle or as a movement, the shadow will give you false positive because there is no really an object, but there is some, in the data mining context, we talk about it as outliers or noise, which will create that you have a classification of something that didn't happen. People can usually live happily when you have true positive and you have some false positive, but people will not use the system if you have false negative. False negative means your system doesn't work, full stop. So this confusion matrix is, as I said, it's a relationship between actual classes or real events and predictions or classifiers or detectors. And in summary, if the event happened and the classifier said the event is there, it's true positive. If the event didn't happen, but the classifier said, or the predictor said the event is there while it's not happening, it's false positive. True positive and false positive, it talks about accuracy. You are not missing any alarms, or you are not missing any events. The minute you start to say, I have false negative, means things happening and I cannot see it, at this point, your system will not work, will not be acceptable. So in our life, false negative is equal to 0 as a rule of thumb. If you have false negative, it means you don't have a classifier. A good example of a phone call. So if the phone rings, what is the likelihood that somebody is calling you? The phone, so if the phone rings, so if I say C1 is the phone ringing, and somebody will be calling you. Okay, so if somebody is calling me, here at the column, C1 is calling me, somebody calling me, no one calling me at not C1. And the predicting class, it will be C1 means I will get a ring and no ring. So if somebody is calling me, I will have a ring. It's true positive, TP. If somebody is not calling me, however, I will have a ring. It's a false positive. What kind of false positive you have? Very straightforward, when you have an alarm. And if the alarm is the same tone as the calling ring, as the ringtone, you will have a false positive because you create an anomaly where when the phone will ring, it will be either somebody calling or you have noise, which is basically your alarm. However, if I would tell you that somebody will call you and the phone will not ring because any issues, will you be using this phone? Does not receive calls. If you say yes for some, it will be always for some time. And if you say no, this is the right answer. And that's why you switch between different carriers, because basically you say, well, so many people are calling me and my phone doesn't ring. So you will be basically changing your phone or changing your carrier. So false negative, it's not characteristics. If you have a false negative inside any kind of applications you do, it means you fail to classify. I have to stop and explain it in this great details because this is not a concept for, as I always say, this is not a concept for data mining. This is a concept for any system you build as computer scientist and computer engineer. If you want to build detectors, you need to avoid false negative. Then you have false positive and true negative. True negatives will, as I said, usually you have false positive and true negative, and sometimes you have true positive and false and true negatives means you basically have a correct detection. You may have from noise some false positive, but if you have false negative, it means you cannot classify. So here is, you can actually compute the confusion matrix. So the actual predictor buying computer is yes, and so this is basically some sort of how you can build the confusion matrix. And at the end of the day, this definition is critical, because if you are an engineer, people will always tell you that. If you work in this area of detection, they always use these terms. However, at the end of the day, it's some statistics. So if I want to look at the accuracy of any, which we described it before, the accuracy is true positive, true negative over all. So how many times you say the class exists and the elements exist, how many times you say it doesn't exist and the element doesn't exist. If the accuracy is 1, this is the ultimate goal. Now, the error rate, it will be false positive plus false negative. So false positive plus false negative, this is the error in rate, and you basically can estimate it as false positive plus false negative overall, or you can do as 1 minus the accuracy. You have to understand one thing. If you run the system and you find out that's computing accuracy and error rate 1 minus accuracy does not cover the whole space, it means you have a false negative, because in a right system or real-time operating system, you will have 1 minus, you don't have false negative. There are some other sensitivity measure, which is sensitivity measure will be the TP over P, which basically is a true positive over the total events happening. So what is the ratio? Sensitivity, usually it's supposed to be in good system 1. Here we talk about data mining, so we talk about specifics, like more statistical models. Now there is a specificity. The specificity basically, it's a how many, it's true, not true, negative over negative, or basically 1 minus false positive over the total, over 1 over minus B. So basically these will be the 2 different variables you can do it. You can also look at precision, recall, and false measure. Precision is exact. So what is how precise is your system? So what they are doing here is they look at this particular matrix of true positive, true negative, false positive, false negative, and they come here and try to compute some kind of accuracy and precision. So here I look at classifier accuracy, I look at error rate, I look at sensitivity, I look at specificity. Here I will look at precision. So the precision is the true positive over true positive plus false positive. So it's basically true positive over true positive and false positive. This is called precision. Recall or completeness, it will be number of positive tuple. Did the classifier classify as positive? Will be basically number of positive tuple. Did the classify it as positive? So it will be basically true positive over true positive plus false negative, which basically here. So as I said, it says here, in a perfect score is equal to 1. The F measure is harmonic, means the precision and recall, which is equal to 2 times precision times recall over precision plus recall. The F beta, a weighted measure, it will be 1 plus beta square. Assign beta time as much as recall times precision time recall, and beta square time precision plus recall. These will be the definitions you have. Do we need to remember these definitions and how it compute? Unfortunately, yes, because if you'll be going to an interview in data mining or data scientist, or even prediction detectors, any kind of this kind of similar, they will be asking you in an interview, yeah, do you know, can you show me the precision, or what precision means? So you say precision means the number of percentage of tuples of the classifier labeled positive are actual positive. Just how much accurate or how much precise I can say. They can say, okay, can you explain the F measure or F beta measure or F1 measure? So all of these definitions you should be able to understand. Now, for the exam or for the tutorial in the current conditions, you may be giving multiple choice or true and false, maybe along that. However, I'm always looking at this material as material for life, not material for course, because as many of you will know, that majority of the learning that I'm doing it is basically open internet and open books and open whatever, because I believe that as a data scientist, you can always look at the information on any Google or any drive. And however, when you be in your company working, they will have their own definitions and they have their own materials. They give you the training. So you have always access to the actual knowledge. However, I'm trying to move that knowledge into useful information. So if I remember this knowledge, I can tell you, if you remember this equation, so here out of this particular section, the definition of the confusion matrix is very critical. Memorize or remember the accuracy, error rate, sensitivity, specificity. Understand what they mean, precision and recall, F measure. So this kind of 5 elements. And by the way, I will not do it for you, but you can do it yourself. If you look at this particular matrix, you may be able to come here and figure out what each one of these, because they are basically related to the diagonal, to the columns and the rows. And then you have the F measure, which basically is a harmonic, or the F measure will be the compound metrics to get more than one weighted metrics in one time, because it talks about precision and recall. There are other hand evaluation of the classifiers. This is the hold out method, which basically, if I have data partitioned into 2 independent sets, the training sets, the random sampling will be the average. I repeat hold k time, and the accuracy will be the average. There is something called cross validation. And cross validation is if I have X mutual exclusive subsets, in which iterations I will be basically get which tuples, and I can do the validations. And then there is the evaluation of the classifier, which basically bootstrap. And the bootstrap will be good because it works with all data sets. Several bootstrapping techniques exist. So here is to give you a quick example. A data set of D tuple is sampled D times with replacement, resulting into training of D samples. The tuples that did not make it into the training end up forming a test set. About 63% of the original data are end up being in the bootstrap, and 36% or 6.8 will be data sets. So basically, the equation will be 1 minus 1 over D to the power D, which basically roughly is 0.3. So if I want to repeat this sample, I will be basically having an equation for all sets K. I will be basically getting, I can compute the accuracy classifiers. The other point we can talk is estimating confidence, or how confidence is my system. So if I want to estimate confidence, I will have a classifier M1 versus M2. So if I have a classifier M1 and another classifier M2, which one has the, which one should I use? So if I use a 10-fold cross-validation to obtain the error between M1 and M2, the error rate is just an estimate of an error on true population of future data. So what's the difference between the two errors rate is just attribute to the chance. So I use a test of statistical confidence, and I will obtain a confidence limit of the estimate. So basically, I will have a classifier, and I can compute the error or the cross-validation of the classifier, each classifier, and then I can figure out which one will have the best likelihood. There is also the null hypothesis, which basically I can perform 10-fold cross-validation. I assume a t-distribution with k1 degree of freedom where k equal to 10. I can use t-test, and the null hypothesis is M1 and M2 are the same, and I can reject it if there is a difference between M1 and M2 is significant or bigger than a specific threshold. So, and I can also have the t-test, which basically if I have one test, I can compare over rounds which one will give me different errors, and then I can compute the average error. These are different techniques. Here is, I can estimate the interval. So here's, I will have different probabilities, and then I can basically estimate the confidence using the t-distribution. The estimation confidence interval, it has its own significance because I can basically select different classifier. And if I want to compute the d-distributions, I will be able to get the confidence. So here, I'm getting the confidence in this area. That's 95% of the population will belong to this particular area. Now, I can also have a model called the ROC curve, and the ROC curve is the receiver operating characteristics curve. It uses for different for visual comparisons. So I can have X and Y, and then I can draw the ROC curve, and from that I can compare between them. So if I have a model and I perform any of these statistics, as you may notice, I can do 10K iteration, I can do cross validation, I can do accuracy, I can do different things. So this model basically, what I can do is I basically want to compare it between two different models. So the issues affecting the model selection, one is accuracy, speed. Accuracy means how accurate the classifier is, how can predict. We spoke about many elements in the accuracy. I can talk about the speed, what's the training time, what's the classification time, or how long I will take to build the tree, and then how long I will visit the tree. I can also speak about how easy to manage the noise and how easy to manage the outliers. I can talk about the scalability. Can it be done in a memory, or it can be done in a disk space? I can talk about the interpretability, which basically how we can look at the insights. There are some other measures. One of them is it incremental or not? I can look at other measures like goodness of results, such as a decision tree size. I can look at different aspects. So if I want to compare between models, there is some set of tools which we explained that you can do it to evaluate the model. So at this point here, we can talk about basic concepts, which we talk about two things. One is classifier, one is clustering techniques. We talked about decision trees. We talked about probability Bayesian classifier methods. We talked about rule-based classifiers. And then we come back and say model evaluation and selection. So which one of these models I will use? As you may notice, that's from the decision tree, we build rules. And using the same tables, we build Bayesian classifiers. So basically, there is some interrelation between these models. It's not independent, which is obvious, because basically you have the same data set, you have the same output, and you try to figure out ways to compute. Now, how to evaluate which model of these you can, we spoke about it briefly. And remember the true positive, true negative, false positive, false negative. Now, I would like to spend some time into techniques to improve classifying accuracy. So there is an ensemble methods to increase the accuracy. So one way to increase the accuracy is basically to combine between different models. So I can use voting schemes. I can use matching criteria. So if I have two different learning models, and the two different learning models will produce two different structures, and then from that point I will pass information, and the information will get classified by both models, and then I can improve the model. So in sample techniques, it uses combination of models to increase the accuracy. I can combine different learning models, and this will create improved models. So there is something called bagging. Bagging means I average the prediction over a collection of a classifier. So I will come and say, if the classifiers, if all of them will give me specific value, I will be basically getting the average. I'll say on the average, this will be that part. There is also something called boosting. Boosting means I will have a weighted vote. So I say this classifier is more accurate. So if this classifier will give me this particular data, I will give it more value. Then there is the ensemble, which basically ensemble means in French means set. And ensemble here means I combine the whole set of heterogeneous classifier. So I will go step by step and explain or having a couple of discussion on each one of them. So basically in bagging, I will do a bootstrap aggregation. So the analogy here is if I want to diagnose by multiple doctors and this give me a majority vote, I will give a set of data tuples. I will train the data, and then I will create my classifiers, models, MJs for each data set. And then when the classifier will return a prediction of a class, I will get the majority of this class. So the prediction can be applied to predict continuous value by taking average values of each prediction for a given set. The accuracy often significantly better than a single classifier because there is an accuracy, or there is a repetition, or you do it second time, third time, fourth time. It doesn't is not the worst for noise data, and for sure it proves the accuracy of the prediction, because when I do more than one prediction, I will increase the accuracy. Boosting, the analogy is to consult several doctors based on a combination of weighted diagnosing. So I will assign weights for different. So I will say I will go to Dr. 1, but because he's like 10 years old or 10 years experience, he will have better weight than a doctor which is 1 year experience. However, a doctor with 30 years will have a much higher weight. So how to boost the work is basically we will have weights assigned to each training tuple. I will have a series of K classifier iterative when I will pay more attention to the training tuple, which is where most not classified, and then I will combine the voting schemes based on this weight, and from that I will be I will be comparing compared with the bagging. Boosting tend to have a greater accuracy because but also it has the risk of outfitting the model with misclassified data. So boosting is better than bagging, because in boosting I know that specific classifiers or specific models will have more accurate data in this particular subset. However, if the more weighted or the more accurate has an error in classifying, it will be basically outfit or misclassify the data. AdaBoost is an algorithm have been produced in 1997. It's just giving an example of how this enhanced systems have been made. It basically give a weight to the error rates. So basically the probability or the weight of the classifier will be 1 minus the error of log 1 of the error of mi minus over the error of all of sigma mi. So here is an example where I try to avoid, or I would try to use the mislabeled to adjust the weighting. Random forest test is another algorithm where each classifier has a decision classifiers, and then during the classification each tree votes, and you can have a random input selection, which basically I can create an F attribute, and from that I can use the cart methodology to grow the tree to maximum size, or I can basically have a random linear combination where I can correlate the data and put them in one. I wouldn't stop that much, and the classification, I wouldn't stop that much on these two different techniques, AdaBoost and random forest. I just show you how you can use the boosting and the bagging into more complex approaches. The classification of a class of imbalanced data set. The class of imbalance problem is rare positive samples, but numerous negative ones. So usually the balance of data means I have 50-50 or 30-60. So what is the likelihood of having a correct medical diagnosing or an oil spill or a fraud? So if I see 1 million people and I say, okay, the average of or the percentage of people have been infected is 0.02%. So in a million, you maybe talk about 20 or 200. So if I see a million and I have 200, it will be rare in a million. So how we can handle situations where we are looking for the 200 in a million, and I'm not really sure when I have the 200 in a million, I cannot, I don't want the data to be driven into always the negative ones. So I assume a balanced distribution, and I will be basically increase the weighting. So there are 3 typical methods for the imbalanced data. One is the oversampling, which basically I resample the data from the positive class. I can undersample, which basically I can randomly eliminate tuples from the negative class. Basically, I can cut the number of samples. I can make a threshold, basically move the decision threshold that the rare class tuple will be easier to classify, which is what we talk about having a weighting the value or weighted contribution to the decision. There is the ensemble techniques as well. And remember, ensemble in French means sets, which basically multi-classifier or a set of classifier. The imbalanced data, our solution to imbalanced data sets is maybe 90% of the actual publications in this area. So anyone will get a new ensembling techniques. He will be basically look at different techniques. Now, as explained today, we talked about basic concepts of classification, which basically 2 concepts. One is to classify, one to cluster. We talked about decision trees, induction, which how to make decisions using tree. We talked about Bayesian classifier, which basically probability based. And if you take statistics or stochastic process or any of these things, you will have deeper knowledge of that. I talked about rule-based classifier. I talked about model evaluation, which model you want to use and how to select it based on accuracy, precision. We talked also about some techniques to improve the classification. Some techniques based on ensemble methods, which basically aggregate multiple classifiers, or techniques to improve classification based on the population when you have low data, or you have that the accurate data is very small. Now, the last thing is the summary. So summary, classification is a form of data analysis that extract model description important classes. Effective and scalable methods has been developed as decision by induction. Evaluation metrics like accuracy, sensitivity, specificity, precision, recall, F measures and F beta measures. You can have k-fold validation. You can have bagging and boosting. Boosting is weighted vote. Bagging is basically averaging. There is a significant test and the ROC test, ROC curves. You can compare different classifiers. No single method is super duper everywhere. There are issues like training, robustness, scalability, interpretability, and you have to consider this when you talk about different angles. The biggest question now is how to study this content into live or into exam. So if you want to understand into life, what you should do is basically you pick up the summary slides, which is slide 70 and 71. And from this summary, you should be able to take the red points and write in the margins what does these points means. So for example, when I talk about decision tree, what does it mean? When I talk about naive Bayesian classifier, remember this I here is double I's because it's just a German name. Rule-based or Australian name. Rule-based classifier, what does it mean? When I talk about accuracy, sensitivity, specificity, precision, recall, remember the evaluation matrix, it talks about true positive, true negative, false positive, false negative. Bagging means averaging, boosting means weighted average. If I go to this slide here, I talk about significant test, ROC curves, comparison between different classifiers. If you read or hear or listen to these particular points, you shouldn't have lots of difficulties into conclude understanding or following on this particular subject. I believe I'm done with the illustration and looking forward if you have any questions or any point for discussions. And if you don't have questions right now, you can always email me or put comments under the video. I hope I'll be able to see them. And I can open the forum for the questions. Okay. Hi, Myrna.
Hi, Doctor.
Do you have questions?
اوكي، هو بس الليكتشر دي احنا هناخدها امتى؟ يعني عايزه اللينك بتاعها.
هناخدها امتى؟ هتاخديها كمان دي اصلا الليكتشر دي موجوده في الكورس. ثانيه واحده. فين
ريكوردينج؟
الريكوردنج ده تاخديه. الليكتشر دي موجوده هنا، موجوده في يا ويك كام كانت. سوري، هي فين؟ هي مش شغاله ليه؟ anyway هي موجوده في يعني البي دي اف موجود، والريكوردنج هتلاقيه يعني يمكن نص ساعه بعد ما نخلص. يمكن نص ساعه بعد ما نخلص او ساعه.
هو اصلا الموديل شغال مع حضرتك ولا لا؟
هو ايه؟
هو الموديل شغال مع حضرتك؟
هو كان شغال قبل الكورس.
شغال عندي. مش شغال عندي.
ايوه، ما هو عندي اهو هوريك ثانيه شير. شايفه ايه بقى اللي انت شايفاه؟ سفاري cannot find the server، صح؟ طيب خلاص هو مش شغال عندي برضه.
تمام.
لا، هو كان شغال الاول، كان شغال لما بدأنا، بس هو انا عايز اقول لك حاجه. هو انا مش قادر اعملها قوي، بس يعني انت لو نزلتي البودكاست الحاجات دي كلها هتنزل على البودكاست، وبتنزل unrestricted. يعني اول ما برفعها هتلاقيها نزلت على البودكاست على طول خلال دي 5 دقائق 10 دقائق. بس النقطه الوحيده ان انت عايزه تفيجري اوت اني فيهم كمبيوتر فيجن، واني فيهم داتا مايننج، واني فيهم اللي هو ال 490، واني فيهم، لان هم الاربع كورسات بينزلوا مع بعض، او اني فيهم يعني ثيوري اوف كومبيوتنج. فانت بس وانت هتعرفي تعرفيهم، يعني انت بسم الله ما شاء الله يعني الناس اللي يعني واعيه قوي وشاطره قوي، فانت you'll be able to figure it out. بالنسبه
دكتور،
ولو انت دخلتي على الجروب بتاع اللي هو المايكروسوفت ستريم، الفيديو لما بيترفع هتلاقيه في الجروب على طول. مش انت موجوده في جروب مايننج؟
مش عارفه بصراحه.
ايه؟
عارفه لو موجوده ولا لا.
اعتقد ان انت موجوده في الجروب بتاع الفيديو بتاع المايكروسوفت ستريم.
تمام، اوكي. هو ماشي، اوكي، خلاص، تمام.
فاديني يمكن نص ساعه ساعه، بس هي حسب النت، لان امبارح النت ما كانش ذا بيست يعني.
الموديل ما يرجعش النهارده.
ايه؟
الموديل ما يرجعش النهارده.
ما انا مش بقول لك، انا هرفعهم على المايكروسوفت ستريم، وممكن ابعت لك ايميل اول ما يترفعوا.
تمام، اوكي، ماشي، اوكي.
اوكي،
شكرا قوي.
عندك اي
تمام
اسئله؟
خلاص. لا لا تمام.
اوكي ماشي، يلا خلاص يبقى احنا كده نبريك الكورس، ولو انت عندك اسئله ابعتها لي في الايميل وانا هحط لك اللي هرفع الكورس right away.
تمام اوكي.
اوكي شكرا. اوكي باي.